Welcome to today's lecture. This is Photoelectricity Part 2. In Part 2, we're starting with photoelectric effect. In Part 1, we looked at the meaning of photoelectricity. We said photoelectricity is the emission of electrons from the surface of a metal when light of sufficiently high frequency shines on it. And we said this phenomenon is called photoelectric effect. We went ahead to look at key terms and definition. We looked at photoelectrons. We said photoelectrons are electrons emitted from a metal surface due to incident light. We looked at photon energy. We said photon energy is the amount of energy carried by a single particle of light, a single quantum of light. We looked at some numerical equations that photon energy is Planck's constant times the frequency of the light. We also looked at C is lambda frequency, that is the speed of electromagnetic radiation is equal to the wavelength of the radiation multiplied by its frequency. We went ahead, we looked at work function. We said work function is the least amount of energy needed for an electron to escape from a metal surface. We said work function W0 is HF0. We also took a summary of what we did in part 1. We said each metal has its own work function. We said low work function metals emit electrons easily. For electrons to be ejected, don't forget, we said the photon energy must be greater than the work function of the metal. Part of the photon energy is used to overcome the work function of the metal, while the remaining energy becomes the energy of the emitted electron. So today we'll be looking at photoelectric effect. So what then is photoelectric effect? This is part 2. Photoelectricity part 2. Photoelectric effect is the emission of electrons from the surface of a metal when light of sufficient frequency falls on it. This phenomenon could not be explained by classical wave theory. So Albert Einstein in 1905 explained it by using the particle nature of light. The classical wave theory states that light behaves purely as wave with energy distributed continuously, but it fails to explain the photoelectric effect. What then is the photoelectric effect? That light could cause electrons to be ejected from the surface of a metal. Now, what are the main assumptions of the classical wave theory? Number one, that light is a wave. That is, it travels as transverse electromagnetic wave. Number 2, assumption that energy is continuous. That is, light energy is spread uniformly over the wave, not in discrete units, separate packets, but it is distributed continuously. Number 3, intensity determines energy. That is, increasing the intensity, the brightness of light, increases the energy delivered. Number 4, intensity determines energy. Increasing the intensity, that is the brightness of light, increases the energy delivered. Number 5, energy transferred is gradual. That is, electrons absorb energy slowly over time from the wave. So all these assumptions summarize the classical wave theory. So in other words, we're saying that light is a wave and that it travels as transverse electromagnetic wave. Number 2, that energy is continuous. In other words, that light energy spread uniformly over the wave is not discrete. That is, the spreading of light energy is not continuous. So the classical wave theory does not look at light as being continuous. Sorry, I beg your pardon. That the classical wave theory sees light as continuous but not discrete. It also sees light as energy that is transferred gradually. And because it is transferred gradually, electrons tend to absorb this energy slowly over time from the wave. So what are the basic assumptions of the classic wave theory? The basic ones, that light is a wave, that the spread of light is continuous, not discrete, that intensity determines energy, and that energy transfer is gradual. These are the basic assumptions of the classical wave theory. This will take us to particle nature of light. The particle nature of light states that light is made up of tiny packets of energy called photons. Each photon carries a definite amount of energy given by E is equal to hf. Remember, we did this in part 1 where we said photon energy is Planck's constant multiplied by the frequency of the radiation, where h is Planck's constant and f is the frequency of light. When light falls on a metal surface, photons transfer their energy to the electron in one collision. If the photon energy is greater than the work function of the metal, electrons are emitted instantly. This explains the photoelectric effect, which could not be explained by classical wave theory. So in summary, we are saying that light energy is quantized, not continuous. Energy depends on frequency, not intensity. In classical wave theory, we are saying that light energy is continuous. In particle wave theory, we are saying light energy is quantized and not continuous. And that energy depends on frequency, not intensity. Energy depends on frequency, not intensity. Again, light energy is continuous for classical wave theory. For particle wave theory, light energy is quantized. Again, for classical wave theory, light is continuous. But particle wave theory, light is quantized. We will explain energy quantization later. In particle wave theory, we are saying that energy depends on frequency. In classical wave theory, we are saying that energy is determined by intensity. In conclusion, light behaves as a stream of particles, photons, during energy transfer, confirming its particle nature. This will take us to Einstein photoelectric equation. Albert Einstein photoelectric equation. Now don't forget that when the electron on the surface of the metal absorb the energy, they become ejected, and a part of the energy from the radiation helps the electrons to be ejected, and the remaining part gives the electron kinetic energy. So this kinetic energy that we refer to as the maximum kinetic energy of ejected or emitted electron is equal to photon energy minus work function. That is, for electrons to be ejected, the photon energy must be greater than the work function. So EK max is used to represent the maximum kinetic energy. Your photon energy is E, and work function is W naught. So EK max is HF minus HF naught. We have done this before. EK max is HC over lambda minus HC over lambda naught. Don't forget your kinetic energy is given as half mv squared, mass of the electron emitted and velocity of the electrons ejected or emitted. So representing or EK max with half mv squared, we have half mv squared is E minus W naught. Half mv squared is HF minus HF naught. Half mv squared is HC over lambda minus HC over lambda naught. If we plot the kinetic energy of the electron against the frequency of light, we will get a graph that looks like this. At this point, we call that the threshold frequency. In our previous class, we looked at threshold frequency, the minimum frequency of the incident radiation that is just sufficient to eject electron from the surface of a metal without giving the electrons kinetic energy. That is, threshold frequency is the minimum frequency of the incident radiation that is just sufficient to eject electrons from the surface of a metal without giving the electrons kinetic energy. Now, meaning of the symbols we have used so far. EK max is HF minus HF naught. EK max is the E minus W naught. Half mv squared is HC over lambda minus HC over lambda naught. H is Planck's constant, which is given as 6.63 times 10 raised to the power minus 34 joules second. F is frequency of incident radiation measured in hertz. F naught, threshold frequency measured in hertz. EK max, maximum kinetic energy of emitted electrons. M, mass of the electrons that are emitted. V, maximum velocity of emitted electrons. I want you to note the following. That F, which is the frequency of the incident light, F naught is threshold frequency. If the frequency of the incident light is less than the threshold frequency, no emission of electrons. If the frequency of the incident light is equal to the threshold frequency, electrons are ejected but no kinetic energy. If frequency of the incident light is greater than the threshold frequency, electrons are emitted and then the electrons take flight, which is kinetic energy. I'll see you in part 3.